the upper half plane has this Poincare metric on it, dx dy over y squared, and associated to this metric, or to this measure, is this version of the Laplacian. So the Laplacian in this setting is y squared times d squared dx squared plus d squared dy squared. You may be familiar with the Euclidean Laplacian, where there's no y squared here, but essentially this y squared is comes up as we're doing everything in sort of in this hyperbolic plane. And we're going to want to know stuff about eigenfunctions of the Laplacian. So let's say that f from the upper half plane to C is an eigenfunction of the Laplacian in the sense that for some scalar lambda, we have that f satisfies this. Now, some authors will have a minus sign here, so be careful. And of course, for all of this, we're using the notation that z is x plus iy. And let's talk about the solutions to this differential equation. So if f is only a function of y, so it's independent of x, then it's pretty straightforward to check that you can take f of y to be y to the s and y to the 1 minus s. As your two solutions. And it's a second order differential equation, so you expect two solutions. If s is 1/2, then this would only give you one solution. So instead your two solutions are y to the 1/2 and y to the 1/2 log y. All right. So those are the easy ones. And then say that f now has some x dependence. So if f, and it turns out that we're going to be interested in functions f that are periodic in x. Periodic and non-constant in x, with period 1, say, then let's write f of z is e to the 2 pi I x, and then some uppercase f 2 pi y, and plugging this into this differential equation here, what we find is that this uppercase f has to satisfy the following equation: second derivative of y plus lambda over y squared. So this is the eigenvalue, or minus the eigenvalue, minus 1 times f of y equals 0. And this doesn't have solutions that are expressible in terms of elementary functions, and functions that come up in like a first course in calculus, for example. But they have some well-known solutions. So the main one that we're gonna be interested in is square root 2 over pi times y, and then here we have what's called a k-Bessel function at s minus 1/2 of y. This is f of y. And here, the k-Bessel function, so y, this is defined according to some integral. Let me go look it up, actually, just to make sure I have it right. It's defined to be 1/2 times the integral from 0 to infinity of e to the minus y t plus t inverse over 2 t to the s dt over t. And there are a lot of equivalent definitions of this. This one I'm getting from Gradstein and Rizek. Let me make sure I know how to spell Rizek. Gradstein and Rizek, equation 8.432.7 with z equals 1. And this is the definition I think I see most often in this field. So it's some integral. It's kind of like the gamma function in that it's some Mellin transform, but it's a little bit trickier than that. And in principle, you can work with this just by working with the definition, and you can figure some stuff out. But in practice, you probably just look it up in some table of integrals, like Gradstein and Rizek. So this is the f that you get, and what that means is that your eigenfunction, which I'll denote w sub s of z, is going to be 2 square root of y k-Bessel function at s minus 1/2 of 2 pi y e to the 2 pi ix. And this is called the Whittaker function. And there are other Whittaker functions that come up in other circumstances when you have a different partial differential equation. So Whittaker functions are a more general thing, but the Whittaker function that we're interested in is this. Now, there's a second solution, but it grows exponentially, and so it's not going to be relevant for us. And so we're going to ignore it. So the the conclusion here is that here when I write s, s times 1 minus s is going to be equal to your eigenvalue. And for these, this is clear, right? If you just differentiate y to the s twice and put a minus sign in front, that's what you get. And so this s here, it's defined by this equation. Okay. So what we end up getting is, and the reference I'm going to give for this is proposition 1.5 in Iwaniec. The textbook Spectral Methods in Automorphic Forms. And proposition says that if f let me write it this way. If f satisfies Laplacian plus lambda of f is 0, so it's an eigenfunction of Laplacian with s defined as such. So it's f is going to have there are going to be multiple requirements for f. The second requirement is that f of z is f of z plus m. For all integer m. So it's periodic in x with period 1. And 3 is that f of z is little o of e to the 2 pi y as y goes to infinity. So it doesn't grow exponentially. Then, well, the point is that we've sort of, with this stuff, we've written out all of the eigenfunctions of Laplacian, right? There's the constant stuff, which is y to the s, y to the 1 minus s, unless you're 1/2. And there are the non-constant ones, which are these Whittaker functions. And so the conclusion to this proposition is that f of z has this Fourier expansion, if you will, and here f0y is a linear combination of y to the s and y to the 1 minus s, or if s is 1/2, y to the 1/2 log y, if f is 1/2, and fn the fn's are constants, and they can't grow too quickly in that. So this is going to be very useful because later on we're going to be considering eigenfunctions of Laplacian that don't grow too quickly and are periodic in M, and this will let us say, hey, they must be of this form. Or again here, W is this Whittaker function. And knowing that they must be of this form, we can start talking about what these individual coefficients are. And these are essentially the Fourier coefficients of the functions that we're going to be caring about. And they'll be very important for studying sequences that we're interested in.